Photoelectric effect. See, when light radiation having sufficiently high frequency is incident on a metal, some electrons are emitted from its surface. This phenomenon is known as photoelectric effect. Let us say that we have a piece of metal on which a light radiation is incident. The light radiation must be having sufficiently high frequency. You can use either ultraviolet radiation or X-rays also. Then what you can observe is some of the electrons are emitted from the surface of the metal and travel with a velocity. This phenomenon is known as photoelectric effect, and there is an experimental demonstration to see the effect. We will see that now. Now, this is an experimental arrangement to demonstrate photoelectric effect. What we are having is a highly evacuated quartz bulb. This is a quartz bulb which is evacuated, that is, there is a perfect vacuum inside the quartz bulb. There are two metal plates which are placed inside the bulb, one cathode and another anode. Both of them are having same dimensions and made up of same metal, and they are separated by some distance. Now, we are connecting an external battery variable power supply between the two terminals, and there is an ammeter also connected in the circuit to see a deflection when a current passes through the circuit. That is how the experimental arrangement is there. Initially, there is no current in the circuit, and you cannot see any deflection in the ammeter, because even though there is a battery connected in the circuit, you have a clear gap between these two, cathode and anode. There is a vacuum between them, and the circuit is open. You cannot expect any current in an open circuit. Now, we will allow some radiation to fall on the cathode. A radiation is made to incident on the cathode. That radiation can be ultraviolet radiation or any higher frequency radiation. Now, immediately as soon as the radiation is incident on the cathode, the ammeter shows a deflection indicating a flow of current in the circuit. What exactly happens is, when the radiation is incident on the cathode, some electrons are emitted from the cathode and they travel towards the anode. You can see this anode is connected to the positive terminal of the battery. The electron is negatively charged particle, therefore it is attracted towards the anode, and the current flow starts taking place in the circuit, and you can see that from the deflection in the ammeter. So, this current is purely driven by the radiation, incident radiation, and that current is known as photocurrent. The electrons are emitted are known as photoelectrons, and the current in the circuit is known as photocurrent. Now, these photoelectrons have various characteristics. We can study the characteristics of photoelectrons by varying the potential difference between the anode and cathode, and so on. First, we will see the effect of applied potential difference on photoelectrons. Now, we will see the effect of applied potential difference on the photocurrent. A graph is plotted between the applied potential difference, which is taken on x-axis, and the photocurrent, which is taken on y-axis. You can see the graph is almost a straight line parallel to x-axis. It implies that the photocurrent is independent of the applied potential difference. This is obvious because the current is driven by the radiation that is incident on the cathode. The current is not driven by the applied potential difference. The potential difference is given in the circuit just to give a direction to the electrons. By itself, the applied potential difference is not producing any current. So, naturally the applied potential difference does not have any effect on the photocurrent. Photocurrent is independent of the applied potential difference, except for a very small change in the initial values. Beyond that one, photocurrent fairly remains constant, and this value is known as saturation current. That is the maximum value that is of photocurrent obtained in this experiment is known as saturation current. That is one point. Next, suppose if you reverse the polarity of the battery, what will happen? That is, cathode is connected to positive terminal and anode is connected to negative terminal. In such case, what will happen? Generally, that is also observed on the graph. The graph looks something like this, that is on the negative x-axis. That is what we can observe. When you reverse the polarity or the negative potential is applied, then the photocurrent gradually decreases, and at a particular value of the potential, it becomes 0. For a particular value of negative applied potential, the photocurrent becomes 0, because once the photoelectron is emitted, see, electron is a negatively charged particle, and if you reverse the polarity, due to that negative potential, the electron is repelled from the anode. So, the electron will not reach the anode itself. Naturally, the photocurrent gradually decreases and becomes 0. That is, when the negative potential is sufficiently large, then the photocurrent becomes 0. You can see that as the negative potential increases, for a particular value of negative potential, the photocurrent has become 0. And this particular negative potential is represented by V naught, and it is called stopping potential. You can say that the negative potential at which the photocurrent becomes 0 is known as stopping potential. So, that is the effect of applied potential difference on the photocurrent. Now, we will see the effect of intensity of radiation on the photocurrent. Like in the given experiment, what we are doing is we are making some radiation to fall on the cathode, and electrons are emitted from the surface, they are reaching the anode, and a current flow takes place in the circuit. That is what the experiment is. Now, if I increase the intensity of radiation, what happens? That is observed in the particular case. Now, once again we will plot a graph between the applied potential difference and the photocurrent. But we will take these variations for various intensities. You can see I1, I2 and I3, they represent different intensities. What you can observe clearly from this one, the saturation current value increases with respect to the intensity. Suppose if I3 is greater than I2 and I2 is greater than I1, obviously as the intensity is increasing, the saturation current value also increases. This is obvious because when the intensity of radiation increases, the number of photons within the radiation also increase. Intensity is nothing but the number of photons per second per unit area. So, when you are increasing the intensity of radiation, what you are actually doing is you are increasing the number of photons. Once the number of photons incident on the metal increases, more number of electrons emitted from the surface of the metal. When the electron number increases, current also increases. Remember, current is nothing but number of electrons that are flowing in the circuit. So, in this particular case, as you increase the intensity of radiation, the number of photons increases. Accordingly, the number of electrons emitted increases. Therefore, photocurrent also increases. That you can observe from the value of saturation current increasing with respect to intensity. That is one observation. Another thing is, when you apply a negative potential, you can see all the three curves for the three different intensities of radiation, they are coinciding with the same point. That is, stopping potential is same for all the three intensities. It implies that stopping potential is independent of intensity of radiation. We can see that later. Stopping potential depends on the frequency of radiation and it is independent of intensity of radiation. For that reason, for all the three intensities, we are having the same stopping potential V naught. Now, we will see the effect of frequency of radiation on the photoelectric effect. In that experiment, we are making some radiation to fall on the metal and some photoelectrons are emitted from the surface of the metal. In that, the radiation, frequency of radiation is gradually increased and what happens to the stopping potential is observed. And we are plotting a graph between the frequency of incident radiation which is taken on x-axis, and then stopping potential which is taken on y-axis. The graph, you can observe this one, a straight line with a slope. From that you can observe that as the frequency of the radiation increases, the stopping potential also increases. Why this happens is, when the frequency of radiation increases, the energy of each photon also increases. Remember, energy of each photon is equal to h nu. In this, nu stands for the frequency of radiation. H is a constant, Planck's constant. Therefore, when you increase the frequency of radiation, energy of each photon also increases. When the energy of photon increases, accordingly that energy is absorbed by the electron in the metal. Therefore, the emitted electron also has a greater energy. It means that the photoelectron is moving with a greater energy. Obviously, in order to stop that electron, you require a greater stopping potential. See, if an electron is moving slowly, you can stop it with a lesser value of stopping potential. But if the same electron is moving with a greater velocity, then you need to stop it with a greater stopping potential. It implies that if the energy of radiation increases, the energy of electron also increases. Accordingly, the stopping potential also increases. That is how the graph clearly shows, as frequency of radiation increases, stopping potential also increases. Another observation which can be made from this graph is that you can observe that there is a particular frequency of incident radiation below which you don't observe any stopping potential, it becomes zero. Why that is happening is, if the incident frequency decreases below certain value, photoelectrons are not emitted. Once that happens, stopping potential becomes zero. And this particular minimum frequency is known as threshold frequency. This is what we call threshold frequency. You can define threshold frequency as the minimum frequency of incident radiation. You can define threshold frequency as the minimum frequency of incident radiation below which the photoelectrons are not emitted is known as threshold frequency, and the corresponding wavelength is known as threshold wavelength. For example, if nu naught is threshold frequency, then threshold wavelength lambda naught will be equal to c by nu naught. Here c stands for velocity of light. So, this is threshold wavelength lambda naught. Now, we will see the effect of photometal in the photoelectric effect experiment. See, in that experiment we are using a metal plate for cathode and anode. Suppose if you replace that cathode metal plate with different metals, then what happens? That you can observe. And with various metal, experiment is conducted, and then a graph is plotted between the frequency of incident radiation which is taken on x-axis and the stopping potential which is taken on y-axis. You can see the graphs for various metals. All of them are having the same slope, and the relation is also same, that is, when frequency increases, the stopping potential also increases. The only difference comes in threshold frequency. For certain metals like potassium, the threshold frequency is less, and for metals like tungsten and platinum, the threshold frequency is high, large. Why this is so is, for certain metals the work function is less, that is, you can easily remove electrons using some smaller energy radiation also. Like alkali metals such as potassium, sodium, all these will emit photoelectrons even with visible light. So, they require less energetic radiation such as visible light. Therefore, their threshold frequency is also less. On the other hand, metals like tungsten and platinum have high value of work function. It implies that it requires greater energy to remove electron from their surfaces. Accordingly, you require a higher energetic radiation such as ultraviolet radiation or X-rays. and their threshold frequency is also greater when compared to alkali metals. So, that is the effect of photometal on the photoelectric effect. Einstein's photoelectric equation. This equation is basically conservation of energy principle that is applied to photoelectric effect. See, in that photoelectric effect, what is happening is you are having a high energetic radiation which is incident on a metal, and some of the electrons are emitted from the surface. Now, suppose if you have an amount of energy contained by each photon, then this energy is absorbed by the electron inside the metal. It is actually, photoelectric effect is actually a collision between the incident photon and the electron in the metal. During the collision process, the energy of the photon is absorbed by the electron in the metal. Now, this energy absorbed by the electron is utilized in two parts. One part of the energy is used to liberate the electron from the surface of the metal. This energy is equal to the work function of the metal. That is one part. The remaining part of energy, if at all there is any excess energy, then that is used as the kinetic energy of the emitted photoelectron. It implies that if we take the sum of work function of the metal and the kinetic energy of the photoelectron, then that should be equated to the energy of the incident photon. Typically, we can show this with this one. Let us say you have a metal and a radiation is incident on this one, radiation having sufficiently high frequency. Now, the radiation consists of number of photons. This is photon, right? The energy of each photon is taken as h nu, and this energy of the photon is absorbed by the electron inside the metal, and it emits from the surface of the metal, and then it starts moving with a particular amount of kinetic energy. The amount of energy used to liberate the electron from the surface of the metal is known as work function, which is represented by phi naught. So, since the energy is conserved, the total amount of energy of the photon h nu should be equal to the sum of the work function of the metal and the kinetic energy of the emitted photoelectron. That is nothing but Einstein's photoelectric equation. That is, the equation looks something like this: h nu is equal to phi naught plus k max. Here k max stands for the kinetic energy of the emitted photoelectron, phi naught stands for the work function of the metal, and h nu is the energy of incident photon. So, this is what we call Einstein's photoelectric equation. Also, the work function phi naught can be represented in terms of threshold frequency as h nu naught. Here nu naught stands for threshold frequency and h stands for Planck's constant. So, obviously, this expression can also be written as h nu is equal to h nu naught plus k max, or we can write this expression as k max is equal to h nu minus h nu naught. So, you can take h as constant common, that is that will become nu minus nu naught. So, this is another way of writing Einstein's photoelectric equation. K max is equal to h into nu minus nu naught. In that, nu stands for the frequency of incident radiation and nu naught stands for the threshold frequency. That is another form of Einstein's photoelectric equation. Photoelectric effect provides an evidence for the particle nature of light radiation. That is, light radiation consists of a stream of particles called photons. The energy of each photon is equal to h nu. Nu stands for the frequency of the radiation. The momentum of a photon is given by h nu by c, where c is the velocity of light. Remember, energy and momentum are the properties of a particle. So, in this experiment, we treat light as a particle. In fact, the photoelectric effect is nothing but a collision between two particles, the photon of the incident radiation and the electron inside the metal. That is a collision between two particles. So, these photons have energy equal to h nu and momentum is equal to h nu by c. The photons are basically electrically neutral. They cannot be deflected by either magnetic field or electric fields. See, the energy of photon is h nu, implies that the energy depends purely on frequency of the radiation and it is independent of intensity of radiation. For example, if you increase the intensity of radiation, what happens is the number of photons in the radiation increases. That is, the number of photons that are incident per unit area per second increases. But each photon will be having the same amount of energy h nu. That is, as long as the frequency of radiation remains the same, the energy of radiation remains constant. Even if you increase the intensity, the energy of radiation will not increase. Now, we will see a problem. The problem is a monochromatic source of light having 20 watts power emits light of wavelength 600 nanometer. What are the number of photons that are emitted by the source in 1 second? Now, to solve the problem, first of all, we will calculate the energy of each photon of the source. Like energy of the photon is given by h nu or hc by lambda. We know that lambda is given in the problem as 600 nanometer. Each nanometer is 10 power minus 9 meter. Therefore, the wavelength is 6 into 10 power minus 7 meters. Now, using that one, we can calculate the energy of each photon as hc by lambda. We will substitute the values of these constants. Planck's constant value 6.62 into 10 power minus 34 Joule second multiplied by c, the velocity of light, as 3 into 10 power 8 meters per second, divided by lambda value as 6 into 10 power minus 7 meters. Now, if you simplify that value, we will get the value of energy of each photon as 3.31 into 10 power minus 19 joules. That is the energy contained by each photon in the radiation. Now, we need to find out the number of photons. Now, the power of the source given as 20 watt. It implies that per every 1 second 20 joules of energy is released by the source. Now, in order to calculate the number of photons, first of all, the energy emitted by the source is 20 joules in 1 second divided by the energy of each photon is 3.31 into 10 power minus 19 joules. Now, if you solve that one, you will get about 6 into 10 power 19 number of photons. That is an approximate value. 6 into 10 power 19 photons are emitted by the source in 1 second.